Hello and welcome to our next 2020 Shell Eco Marathon virtual learning session, today with Altair Engineering. My name is Norman Koch and I'm the Global General Manager of Shell Eco Marathon. First of all, I would like to start off with thanking all of you for your flexibility and understanding as we evolved the Shell Eco Marathon program due to the impact of COVID-19. As this situation continues to change, the safety and health of our Shell Eco Marathon participants and organizing teams remains our top priority. And given this current status, we're excited to have you now all with us today in this new digital environment to kick off our virtual learning sessions, all from the safety of your homes. Today, you'll be hearing from Eric Larson from Altair Engineering about creating lightweight optimized designs. Altair is a global technology company that provides software and cloud solutions in product development, high-performance computing, and data analytics. Altair supports the Shell Eco Marathon by supplying licenses, training, and support for Altair HyperWorks to all teams competing in the Shell Eco Marathon program. Eric is the technical account manager for education in Altair Engineering. He's been with Altair for 13 years and studied mechanical engineering at the Michigan Technological University and has 30 years of experience in product design and analysis. So welcome, Eric, to the call, and we look forward to hearing from you in just a few moments. Just a bit of housekeeping before this call. We would, of course, like to make sure it is an as interactive session as possible. So if you have any questions, and I hope you have lots for Eric throughout this presentation, please go on your browser to the website menti.com and enter the code shown below on the screen. On menti.com, you'll be able to post your questions and also see others' questions and give a thumbs up to any question you think is important to answer, so they raise up to the top of the queue. If by any chance you have any issues accessing Menti, you can also post your questions on the YouTube comment box to the right of the live streams once you're logged into YouTube. Eric from Altair will then be answering your questions after the presentation part of this live stream. So, and just in case, let me not forget, as this is a live stream, if for any reasons we run into any technical difficulties, please be patient with us and bear with us while we sort out the issue as quickly as we can. And that's all from me now. I'll hand over to Eric from Altair, who officially will kick off the session now. Eric, over to you.
Excellent. Thank you so much, Norman, for that very nice introduction. I, too, would like to extend my gratitude for those of you who have taken the time to join us here today. I know this wasn't the Eco Marathon we were hoping for, but due to current conditions and some tremendous effort on the part of Shell, who I'm also very, very thankful to, they've put together this fabulous virtual event that we can enjoy in this time of self-quarantine. So a bit about Altair and our background with the Shell Eco Marathon. This is our 4th year of being proud sponsors and partners of the Shell Eco Marathon. But even before we became official partners and sponsors, we have been supporting Super Mileage and other teams for many, many years through as Norman mentioned, through the providing of software licenses and support. And we support vehicle design. We support with a vehicle design award, and we sponsor teams. And with our CFD capabilities, our structural analysis and optimization, we're a great fit for any competitive design team, especially those looking to improve vehicle performance in terms of fuel economy and energy efficiency. So I'd like to kick off my presentation here with just about 4 slides. I do promise you that we'll keep these brief. I know slides aren't the most exciting thing in the world. I like to do my demonstrations live, but there are a couple of slides that kind of let you know what Inspire is all about, what it does, its capabilities, the advantages of it, and then we'll move into a bit over an hour of a presentation of how to use it, give you enough information to kind of hit the ground running and utilizing Inspire to make your designs better. So Inspire is a tool to allow you to very easily, very quickly, and very, very accurately provide structural simulations or conduct structural simulations, and more importantly, allow you to create lightweight optimized parts. So if optimization, generative design is not something you're overly familiar with, this slide kind of demonstrates the process that we go through with Inspire. So on the left here, we see the initial design. This is a part, and this picture does not do it justice. This part is very large and very, very heavy. It is a support for a truck, a suspension support member for a truck. And it's very well designed. I'm sure it has a very high factor of safety and a very good design. But as we move into a world where we're looking for greener parts, we're looking for parts that are more efficient, that are cheaper to make because of lower material utilization, that are greener in the fact that we want our vehicles to be more fuel economical. we want parts that are strong enough to do the task that we're looking to do, but lighter than they are right now. And this beast of a casting, this Liebherr group decided they wanted to take a look at it and see how they could improve the design. And so they took this initial design and through using the steps that we're going to go through shortly in Inspire, were able to come up with this design right here, which you can see is a similar to, but a radical deviation from the original design, taking material out that Inspire was able to deem as unnecessary to the structural behavior of this part. And from that, engineers were able to then engineer this shape from it, a manufacturable design that took 55% of the mass out of that. It's not a typo. It's very, it's common for us to be able to take 55 or even more. Very, very common for us to be able to take, say, 25 to 50% of the mass out of your current design parts, but make them as structurally sound as possible. This next slide highlights another of the advantages that you can achieve by using Inspire, and that's a reduction in design time. Designing a part takes time, perhaps a substantial amount of time. This aircraft door hinge here, using their conventional design process, they ended up with a part that had a mass of 9.15 kilograms, and it took them 3 months to design, coming up with original concepts, running it virtually through testing, perhaps even physical testing, determining problems, coming up with new designs. It took them 3 months to do it. But using the optimization-driven design process, simulation-driven design process, they were able to reduce that mass to 7.5 kilograms, and more importantly, reduce the production or the design process from 3 months all the way down to 3 weeks. And we can achieve that because utilizing simulation in our design process allows us to speed it up, because we're virtualizing so much of the testing and we're virtualizing much of the design process. Another key aspect of any design is design for manufacturability. Not only do we want parts that weigh less, that cost less to make, that are strong, but the most incredibly designed part in all of history is completely useless to us if we can't make it. So another feature of Inspire is the ability to include manufacturing constraints. So constraints that say we're looking to manufacture this part using this process, we need to make sure that the design that ultimately is developed is capable of being designed or being manufactured using the processes that we have. So Inspire understands the limitations of certain manufacturing processes and works that into the design. So a tremendous weight savings and a part that can be manufactured. Finally here, the last key aspect of any design is reliability. We're going to set some design criteria, structure, or factors that have to be met. In this case, this is a part that was launched into space. This is an antenna bracket for a satellite that's actually currently orbiting the Earth right now. And not only did they want to reduce the weight of this part, which they did, they brought the part down from 1.62, 1.63 kilograms down to a bit over or a bit under 9.94 kilograms, a 42% weight reduction. But this part was expected to see tremendous forces, tremendous stresses during the launch process. And they needed to be assured that with this weight reduction, they were creating a part that could meet those very rigid design criteria. Because once you press the button and that spaceship or that rocket ship takes off, if that part breaks, that's it. There's no going up there to fix it. So not only were they able to achieve a 42% weight reduction, they made sure that it met all of the static strength and stiffness behavior that were required. And I'm happy to announce that this part did survive launch and is currently orbiting the Earth, providing data back from that antenna exactly as they were hoping. So with that, I'd like to move on to a direct demonstration of the software. I'm going to open that up right now, and we're going to show you all of the processes that are necessary to achieve these sort of design savings using Inspire. So over the next hour, 5-10 minutes, we're going to run through the basics of this. And interestingly enough, Inspire is so easy to use that even given this limited amount of time, I'm going to provide you enough information to hit the ground running with Inspire, should you choose to start utilizing it to better your designs, create stronger, create lighter weight designs. Before we get into loading up a part, just to kind of take you around the interface here, when you first install Inspire, it's going to look something like this. We have our pull-down menus up at the top, of course, our file, where we can open, create new parts, import, edit, where we can make some changes, view, where we can manipulate the view. And one of the things that I always do is I turn on this model browser or click F2 and turn on the property editor or click F3, because the information that you're going to get in here about your model is very valuable, definitely worth the slight loss in design space. Those will be off by, or the visualization space, those will be off by design or by default when you install it, but it's very easy to turn them on. And once you have them on, Inspire remembers the configuration state you had for the view, so it will maintain that every time you bring Inspire up. Past the view here, we have geometry, structure, motion, manufacture, print 3D. These are following the standard ribbon structure that is very commonly used in Windows-based softwares these days, where these just change the configuration of the icon ribbon across the top here. So geometry is going to give me all of my functions that deal with geometry creation and manipulation. Structure, the tools to allow me to set up and run analyses and optimizations. Motion, to do dynamic multi-body simulations, which we'll talk a little bit about at the end. Manufacture, which will allow me to do simulations, porosity and thinning, so casting and stamping. And then print 3D, where we can take our designs and prepare them for 3D printing directly here within Inspire. Some other features around here are a little triad. If I click on any of these, it alters the view. We'll see that better once we bring up a part. And some of the features down here we'll talk about when we bring up a part. So we may as well do that now. I'm going to come up here to the file pull down, and I'm going to select this exercise 2_B. This is a parasolid file. You'll see when we bring geometry into Inspire, if I come here to File, Open, we do support all of the popular CAD packages in their native format. So whatever CAD system you're using, we will support that native format, so you can bring that in, or you can utilize one of the intermediate formats, like iJustStep or Parasolid. We support those as well. And all of your design structure, all of your organization, assembly names, part names, that's all going to be maintained when you bring the file into Inspire. So this part right here, this is an aircraft door hinge bracket. In fact, if you remember back to that slide that we showed, this is the bracket that allows that hinge, that aircraft door hinge, to work. Two of these get mounted on the frame of the aircraft, two of them get mounted on the door of the aircraft, and the hinge is going to go between them, and that allows that interesting behavior of an aircraft door, where it kind of opens, comes in a little bit, turns to the side, and then goes and rests against the side of the aircraft. So ultimately, we want to take a look at redesigning this part, coming up with an optimized, lightweight design of this part. And we can keep track of the weight, the mass of this part over here on the side. You can see right now it says it's 4.2, about 7 kilograms. And if I select the part right here, you can see the material defined is steel ASI 304. Inspire always assigns a default material, and the default material by default is steel 304. I can change that by right-clicking on this part, selecting material, and perusing down this list here. So everything from the top here, that steel 304, all the way through plastic nylon, are materials that come in the default library within Inspire. And the one I'm going to select is aluminum 7075 T6, a very common aviation grade aluminum. And you can see by selecting that, I already reduced the weight on this, brought it to about 1.5 kilograms. But assigning the appropriate material is very important to make sure that our structural results and our optimization results are correct. And if you have material specifications that don't fall into one of those values or one of those types that are in our library, it's very easy to add a custom material to Inspire. I just come here to the structure ribbon, come to materials. In its main default tab here, it's going to show you all the parts in your model and the material that they have been defined. I can view that material library, or what I'm going to do is I'm going to come to my materials, and from here I can click the little plus button. You see now have material 2, and that's going to be a custom material. All I have to do, I can come here and click on it. I can rename it to whatever I want, and then I add the specifications for the material. So my Young's modulus, my nu, my Poisson's ratio, my density, the yield stress, and coefficient of thermal expansion if you're looking to do a thermal, analysis. And when I put that custom material in, now when I right click on this and I select material, you see that material 2 along with my other custom materials are available in that drop down list, and they will stay there unless I decide to delete that material from my database. So if you have your material specifications, by all means create a custom material, and that guarantees that you're getting the best possible results by utilizing the specifications of your specific material. So with material defined, I can now begin the action of, or the process of setting this up for a structural analysis. What I want to do is I want to run an analysis on this. I want to see how this part is going to behave in its current form. I have a sneaking suspicion that there's room for improvement on this, but the only way that I can know that is to find out where we are right now. So I'm going to set up a baseline analysis on this, get an idea of the design of the part, how it's behaving right now, and then I can use that to compare the results and develop the parameters necessary to run an optimization and make this part lighter. And we'll get into setting up that analysis in just a second, but one of the more important things to know early on is how to manipulate your model. So we need to pan, we need to zoom, we need to rotate. Rotation in Inspire, the default rotation is to hold down the middle mouse button or the clickable scroll wheel and move it around. And we get this trackball style rotation where it's rotating about that little X in the center there. And as I move this around, I get my rotation. To pan it, I just hold my right mouse button down, and as I move my cursor around the screen, my part moves. And then finally, to zoom, I pull my scroll wheel toward me and I zoom in, and it does use the pointer as a focus. So whatever the pointer is hovering over, it will zoom in to that region of the part, and then pushing the wheel away zooms out. And those are the default parameters for the mouse control within Inspire. One of the biggest problems that people encounter as they move from one GUI-based software to another, from a CAD system to analysis system to another CAD system or whatever, is the fact that every single GUI-based system tends to have their own unique way of manipulating your part. The three big ones, panning, zooming, and rotating. And none of them ever seem to be the same as any other software. So we do have our own default version of manipulation, but we want to make sure that your transition from a CAD software into Inspire is as seamless as possible. So what we can do is we can come back here to the File pull down, come to Preferences, I can click on that, and then if I come to Mouse Controls, you'll see it lists all of my standard, my right, middle, and left plus right. I can change those to whatever I want, as well as the modifiers with Control, Shift, and Alt. Or if I have a software that I'm comfortable with, a CAD software I'm comfortable with, so be it CATIA, UG, SolidWorks, whatever, you can select that from this pull down, and it will change the mouse controls to mimic those exact controls in that CAD-based software. So I know SolidWorks is a very common software, CAD software used in academia. So by changing it to SolidWorks, now I can manipulate my models in SolidWorks using whatever mouse controls they have, and when I come into Inspire, the mouse controls will be exactly the same, so it becomes a seamless transition from SolidWorks into Inspire or any of the other CAD packages that we support in here, and we support all the big ones. Now, I don't use a CAD package, so I'm just going to go back to the default. I'm comfortable with that. But if I had changed it, I'd click OK, and we'd be good to go. So now I've defined the material definition of my part here, and I'm ready to begin setting up the analysis. As I said, we're going to run this baseline analysis. We're going to see how this design behaves right now and use that information to guide us in our optimization. It is not necessary to run a baseline analysis first. You don't have to. We could hop directly into optimization if you want. But in the case of this part, I want to see where we are at first, and then we'll move on to the optimization portion of it. So to run a linear static analysis is a couple of things. First of all, it is a linear analysis, so we are assuming the material is isotropic homogeneous, and we're dealing with it just in the linear, the elastic portion of the stress-strain curve. So all of the results are accurate up until the yield point of the material, when the part would become nonlinear, and at the moment, Inspire does not support nonlinear materials. OptiStruct, which is the solver behind Inspire, does support nonlinear materials, but we have not incorporated that functionality into Inspire yet. It is coming eventually, but for right now, we have to assume the linearity of materials. And it is a linear static analysis. So the static portion of it means that the part can't dynamically move. It has to stay in place. It can locally deform, but it cannot rigidly move. And to accomplish that, we come to the structure ribbon, and we're going to assign supports to our model. The supports, or oftentimes referred to as constraints, are a way of holding the part in place. And if I come to my loads icon here, I can define my support. So all of the different types of standard loads are in the loads icon. But to make sure that we can incorporate all the functionality that we need to within Inspire, and yet still keep the interface as intuitive as possible, make the icons as large as possible, what we decided to do was come up with this idea of a multi-function icon. So the multifunction icon in the case of the loads means that all of the different loads, constraints, forces, pressures, and torques are all located on this icon. So I don't click it and then get some sort of submenu. I actually can select it from different locations on the icon, and I get a different function. So down here, I get my supports, my point stresses, or point forces, my distributed pressures, or my moments, my torques. So if I come here to my support, you see my pointer now takes on that little modifier. It looks like a little cone. It lets me know that I have moved into the function to create supports, to create constraints within my model. And this little help pointer here says select a point, edge, face, or hole. The 4 different types of geometry that I can apply that support to. As I move over my part, you'll see that pointer modifies slightly again. I get a little plane on top of it, or a line on top of it, a point, or a hole. So if I select this plane, this face, it will put an icon at the exact location where I clicked it. But the fact that this entire surface now turns red when I select that icon means that that entire surface is following that constraint. And right now it is a fully constrained, a full Encastra constraint. All of the degrees of freedom are restricted. It cannot move or rotate in any direction. Time when we're going to want to create kind of a custom constraining system where not all of the constraints are fully constrained, and I can free up different degrees of freedom from this by just double clicking on that icon. It will pop up these 3 little arrows, and whichever arrow I select will turn green. And now as I right click to get out of here, you see my constraint, my support icon has modified to include these little rollers, indicating that this part is now free to roll, free to move, slide in plane but along the y-axis. If I need it to slide in a direction that's not one of the cardinal axes, all I have to do is double click on it and come to this move support here. And now I can rotate that in any direction that I want, either 5 degrees at a time by grabbing that little curve and rotating it, or grabbing it, rotating it, and typing in a unique number. And now it will align to 37 degrees off of the y-axis, and you see the little roller balls, or the little roller wheels, are accurately representing the degree of the direction that it's free to move in. If all I want this constraint to do is prevent motion in the Z, the up and down, double click it again, free up the other planar direction. Now I get a caster wheel on it, a caster ball on it, indicating that this is free to move in plane, but not out of plane. And that will be applied to the entirety of that face. Now I want to apply this, I could, like I mentioned, I could do that to a line, a point, or a face, but I want to apply this to a hole. These brackets are going to be bolted to the frame of the aircraft, 2 of them, and then bolted to the door of the aircraft, 2 of them, and then the hinge is going to go between them. So I'm going to simulate this being held in place by putting my supports, putting my constraints on the holes where the bolts are going to go through. And you'll see when I do that, I get a slightly different looking constraint, and that's because Inspire is now recognizing this as a hole and taking advantage of the unique constraints that are set on holes, which are, when we have a hole, in almost every case, we're going to constrain it by putting a pin through it, a clip pin, or a bolt. And that means that when I double click on it to release degrees, the 2 I get now are rotation about the axis, movement along the axis, but that will always maintain a constraint, a restriction of movement normal to the axis. And if I turn these off now, I've bolted, it's not moving. So my part's set for the static portion of it. The next thing I need to do is apply some loads to this. I want to make sure that I accurately simulate the loads as this is going to see. But before we do that, I'd just like to remind you that if you have questions, and I do hope you have questions, I very much enjoy answering them, and we'll set aside a good half an hour or more to deal with your questions at the end of this. But please remember to go to menti.com and enter in that code that they were showing earlier, 562036. And I believe I see it now at the bottom of the screen. Enter that code in, and you'll be able to ask your questions. And Norman will join us back at the end, and he will pose your questions to me, and we'll make sure that every single one of your questions gets answered. Okay, so moving along, the next thing that we need to do is assign some sort of force to this. Right now, all we'd be doing is analyzing it sitting in place, which isn't going to give us much information at all. So a proper analysis is going to have some sort of loading condition, some sort of situation that we want to analyze. And we're going to come back to our loads icon. And we finish our support, so we'll move up top here. And you'll see we have a force, which is a force that's going to be applied to a point, a line, or a face, a distributed pressure load, which is going to be distributed across a face or a line, or we have a torque or a momentum there. I'm going to choose the applied force. And again, I'm asked to apply it to a point, an edge, a face, or a hole. If I select that face on top, just like with the constraint, it's going to put an icon there at the location where I clicked. But again, just like the support, because that entire face is highlighted in red, that force, whatever value I put in here, is going to be evenly distributed across that entire face. In fact, if I hover over it, you'll see it tells me the force, but then it tells me the equivalent pressure based upon the overall area of that face. And just like I could with the constraints, I can orient this in any of the cardinal directions, plus or minus, as well as move that, rotate it in any direction that I want based upon these little manipulation icons. Or I can, oops, get out of this, select that again. I can come in here and enter in the vector components of that, and then enter in the separate magnitude up here at the top. That applies again to a face, a point, or a line. What we're going to do is simulate the hinge being attached to this at this hole right here, and I can apply that force to the hole. When I select a hole, what's going to do is it's going to put that force at the center of the hole and then attach it to the entire inner surface of that cylinder. So even though you don't see any physical attachment there, the fact that when I select that and the entire inner surface here is highlighted is evidence that that will be applied to that entire inner surface. And it is pointed in the direction that I want it to be, so that's good. Now I just need to assign a magnitude to it. And I could come in here and say, okay, I want this to be 2,000, click enter, and it says newtons. Now, how did it know I wanted newtons? Well, that's controlled down here in the lower right-hand corner by what we call our units systems here. You'll see all of the common unit systems. If you're not familiar with finite element analysis, we have what we call unit systems. They consist of a unit of force, a unit of time, and a unit of distance. And then all other units are derived from those three main units. And the most popular ones are the millimeter newton second and the inch pounds force second. So we're in the millimeter newton second in reporting our masses in kilograms. And that meant when I put in 2,000 there, it made it 2,000 Newton load. And I'm happy with that. I'm happy with the direction. So I'm going to right click to get out of here. But there are two scenarios that this bracket can see. One scenario, which we've simulated here, is it being bolted to the door of the aircraft and that aircraft door being opened. And now it is being pulled down as a result of the mass of the door. So the mass of the door is pulling down on this. But there's another scenario when the aircraft door is closed and that hinge is pulling, or that hinge is pulling on this bracket, keeping the door closed. And so I need to come here to my force, and I'm going to apply another force to the inside of this. It's pointing in that direction. I'm going to click minus, so it's pointed out there. And again, I can put in the value. Now, let's say, for instance, that I didn't know the value of the force in newtons. Somebody had supplied it to me in pounds force. Well, I have a couple of options there. If I happen to know the conversion offhand, I could just type into a calculator, or many calculators can do conversions for you. Probably one of the more popular things to do is go to our friend Google and type in what is 500 pounds force in newtons, and Google, the all-knowing being, comes back and tells us what that is. But we want to, again, make units as easy as possible within Inspire, so I can type in 500. And if I clicked enter now, it would be 500 newtons. But if instead of clicking enter, I type in LBF for pounds force, and then click enter, it automatically does the conversion to whatever value of force, whatever unit of force I'm utilizing in this analysis. And the other very cool thing about units is they are truly seamless. So I can come here and switch to any unit system that I want, and it will automatically update all of the measurements on my part. So we'll put that there. You see it says 2.75591, a rather odd number there, but you'll see why in a second. If I come to my force, you see it says it's now 449.62 pounds force. So it is reporting it in the unit that I have there. Everything in this part has been adjusted to this new unit, including the material specification. So I can switch units at any point in time. But I do want to be running this in millimeter Newton second, so I can come back to that. And you'll see now the distance there is 70 millimeters. So obviously this was designed using the millimeters as a distance using a metric unit system. But units are truly seamless. You can change them at any point in time and it will have no detrimental effect on your model. It will just change it to the new unit system and everything will be exactly the same. So let me come down here, and just so that's not bothering us, I can turn that measurement off. It stays, but I can turn the display state on or off. Okay, so I've got my two forces on here, but the remaining problem that I have now is both of those forces are going to act together. And I don't want that. There's no way that the door can be open and closed at the same time. Those forces will always act independently. But I do want to see how each of them alters my part, the behavior of my part when each of them is applied. And more importantly, when I get to my optimization, I need to make sure that my optimized shape takes both of those scenarios into account. So what I can do is I can come back to my loads icon, and as opposed to picking anything on there, I'm going to pick this little chart here. And this provides us what we call our load cases. So what load cases are individual analyses. I said I had two, so I'm going to add another one here. It says load case 2, and now I can just pick the supports I want to use in this, which of course are all the supports, and pick the force I want to use, and then come here and turn off the force in that one. And now I'm going to run two analyses. When I click the run button, both of these will run. And again, more importantly, when I click the optimize button, when we get to that point, the part will be optimized for both of these design scenarios. And I can add as many load cases as I want without adversely affecting the time of the analysis. It will obviously increase the optimization time the more things that I add to it. But say I want to simulate two of the bolts failing. The easiest way to do that is just not include them. So I'll skip 2 and 3. You can see that's these two bolts here, which are highlighting as I move over it. So I skip those, and I'll just grab the rest of the bolts, and we'll grab, say, that force right there. And now I've simulated this, or I'm going to simulate it, not taking into account these constraints. So it will be as if those bolts have failed. And with that, now that I've separated these, I have everything set and ready for my analysis. So you can see, had I not been talking through the entire thing, from the time that I brought the geometry in to the time that I'm going to come up here and click run to run the analysis, I could have had this done in about a minute or maybe a minute and a half. It's that easy to set up an analysis in Inspire. So I'm going to come to my Analyze button. A few more parameters I have to set, the first of which is the name. This is the name of this analysis. It will not affect the model name, but especially if you're going to be running multiple analyses, multiple simulations, it's often best to rename the simulation so that you can distinguish it and know what was done with that. So I could say this is baseline analysis for optimization. I'll leave it as is, though, because I'm not planning on running any other analyses. The next thing down here, element size. Now, you're never going to see an element within Inspire. Inspire is designed to put all of the difficult tasks, the meshing and everything regarding that in the background. So while you're not going to see an element, we do have full control over the mesh. Inspire has automated using SimLab in the background and our geometry analysis tools, feature analysis tools. It has calculated the best possible element size. You can change that if you want, but I'm going to leave it as is. The next thing I have here are normal modes. So do I want to analyze, do I want to know what the natural frequencies of this part are? I can turn that on. The default is to retrieve 10 modes and then indicate whether I want this to be supported or unsupported. So right now it's no support, so I just get the basic natural frequencies of this. But if I want to understand the natural frequencies when it's loaded or when it's attached to the aircraft, I can pick either load case 1, 2, or 3. Load case 1 and 2 use all 6 supports, so they'll be exactly the same. But load case 3 would tell me the resonant frequency assuming these bolts were no longer affecting it. But I'll leave it as an unsupported or free analysis. We can do buckling modes, and just like normal, it's going to pull the number of modes we request, and then ask us which load case we want to do. Speed versus accuracy, I'm going to leave this on more accurate. Again, referencing elements, what more accurate means, if you're familiar with elements, is you're going to get second order or cubic or quadratic tetrahedral elements, whereas faster is going to provide you linear or first order tetrahedral elements. It is always best to leave it on more accurate. Your results are going to be substantially more accurate using those quadratic elements. But if you find that your analysis is going to take too long, you need some quick down and dirty results, and you're not, betting the farm on the results, you can do faster. You'll get them faster, but just realize that there's going to be some error built in there because of the less accurate element choice. Contacts, will come back to that. Gravity, do I want to include gravity in my simulation? Under normal circumstances, I would not. This part is relatively compact, so the gravitational effects are going to be completely unreadable. It's not going to have any discernible effect on this part. But if I had some, if this nose were cantilevered out severely, I might want to include gravity. And if I do, then I just need to come up here to my gravity icon and make sure it's pointing in the correct direction. In this case, the y-axis, and I can do plus minus. I can also affect the gravitational acceleration. There's no need to, as that is set to Earth standard. But if you're ever looking to analyze something that's not going to be seeing Earth standard gravitational acceleration, you can alter that value. If you're looking to do G-loading, do not do it by altering this. We do have G-loading capabilities up here, and we'll talk about that in a minute. I'm not going to include the gravity just because it does add a little bit of time to the analysis, and like I said, it's not going to have any discernible effects. The last option here is to include all of the load cases or turn them off if you don't need them, and then click Run. Now what's going to happen in the background here is have some enterprise level softwares, some traditional FE tools, SimLab, a tetrahedral meshing tool, feature-based tetrahedral meshing tool, HyperMesh, a very high-end meshing and pre-processing tool, and then OptiStruct, our analysis and optimization. It is utilizing those corporate level traditional FE tools in the background here. You don't even have to have them installed, but using those guarantees better than any other system like this that your results are as accurate as possible, because it is using our tried and true analysis and optimization tools. But while this is plodding along, and it should only take a couple of minutes, we'll discuss some of the other loading capabilities we have here. The first is what we call the enforced displacement. Say I don't know the loads that are going to go on here, but someone has hung a door off of this and they can tell me that that point right there is going to move 4 millimeters in the negative Z direction. I can put that there. What will happen is it will force that point to move 4 millimeters, and I can then analyze the stress as a result of that point moving. I don't want that, so let's delete it. I can do angular velocities, angular accelerations, G-loading, as I mentioned, so I can click on the part and say I want this to be a 5G load on this part. And then, of course, I'd need to make sure gravity was pointing in the right direction and turn on the gravitational effects. So I get my G-load there. And if I hover over it, you can see it says G-load 2 5G. I can also do temperature loading. So if I click on that and then click on the part, this is a delta T. So it's telling me that irrelevant of what the temperature was to begin with, it's assuming that is the 0 state. It is increasing at 150 K, and it would subsequently enlarge as a result of that, and we'd see the stresses as a result of this part enlarging. Or if I were to say negative 150 K, then it would contract because of a lower temperature. So this is not heat transfer, but it is heat as a load. Last but not least, I can also assign structural masses to it. So say I didn't know the force, I could put a mass on here. When I put mass on there, I have the ability to define the CG. I'd orient that with the CG, make sure it had the mass, and then connect it to that hole right there. And what that would do, so let me move this off of here. What that would do is it would simulate the door hanging off of this and deforming that as a result of this. So no matter what information you have, you can create an accurate analysis and get accurate results. And as you can see here, we now have our results. So I'm going to come here, click that little flag. I can see both of my load, or all three of my load cases. We'll stick with load case 1 for right now. I can animate that. This is a deformed animation. So it will, scaled animation. So it will automatically scale that up by a calculated amount so that you can see the behavior of that. This is not the actual deformation of this part, but the graph, the legend is accurate. So what this is going to do is it's going to tell me that, or let me know what the behavior of this part is. Because if I didn't scale it, if I just left it, and I'll set it for 1, you can see that I can barely see. I really have to zoom in very far to see the behavior of this, and I have to zoom in so far I can't even see where I'm at. So it doesn't allow me to understand the overall effects of that load, which is why we automatically scale up. But don't worry, whatever the scale may be, the legend is correct. And I can change this to von Mises stress, see the von Mises stress. I can change to the different load cases. Oops, we'll skip normal modes for right now. There we go. So this is the one where the bolts have failed. And then I can see the normal modes. So this will show me the mode shapes as well as the frequencies they're going to vibrate at. And so we can see all of the different mode shapes here. Now, last but not least, what I'm going to do is come back here and come to load case 2, and I'm going to change my result type to factor of safety. So factor of safety is going to tell me how safe my part is. It's going to take a look at the stress of my part and then compare that to the yield stress value that was put into my material definition. And keep in mind, when we're talking about a linear static analysis, yield stress is the failure criteria that we usually look to. And I can isolate values by their factor of safety. So if I grab this little slider and move it down, you see once I move off of 6 times factor of safety, everything disappears, which tells me that this entire part has at least a 6 times factor of safety, which is not good. So not good, when I say not good, I'm not talking about not good in the safety standpoint. This part is obviously really safe. Based upon the loading conditions that I place on it, this part is never going to fail. But it's bad because if I have a 6 times or higher safety factor, it means I've over-designed my part. There is no way I'm going to encounter a scenario where I'm seeing 6 times the loading that I'm predicting. A good safety factor is usually somewhere around 1.5 to 2.0. And what this tells me now is there's a lot of room for improvement here. And that's going to lead us into the next segment, optimization. Before we move on, though, let me remind you that you have the ability to ask questions if you go to menti.com and enter in that code, the 562036. That code will tell you, or will allow you to ask questions, and we will get to them towards the end of this. So please take advantage of that. I'm looking forward to answering your questions. So we'll move into the optimization realm of this, but before we do that, we need to talk about one more thing, and that is connections. This is one single part, so there's really no connections to this, but a large portion of the types of analyses we're going to do are going to involve multi-part assemblies, or even if it's not an assembly, the potential for a single part to be broken up into separate pieces. And Inspire can handle that with no problem whatsoever. The way that Inspire does that is through the use of contacts. And what Inspire does by default to always make sure that your model can be analyzed is any adjacent solids. So I've got, say, this solid here and this solid here. They're touching each other, adjacent to each other, so they are bonded together. And we can visualize that by coming to this contacts function here within structure. And you'll see I get this blue surface right there. That tells me that this is bonded to that. It's as if I put an infinitely strong super glue on each of the pieces, stuck them together, and now they're never coming apart. They will act as one part. So because this is entirely bonded together, this part is analytical. Even though it's made up of, say, 20, 30, maybe more different parts, this is entirely analytical because all of the parts are bonded together. So I could run it like this. But there is a bit of one slight downside to the bonding is that while it will analyze it and while the results will be pretty good, in complex situations like this, where I've got, say, this top plate, let me move out of this phase. I've got this top plate, I've got this bottom plate, and this piece wedged in between it, along with these bolts that are running through there, bolts and screws. It's the bolts and the screws that are going to carry that force from this arm to these plates. But based upon how I've got it defined here, it actually will carry through these contact surfaces, and the bolts will become almost irrelevant. In fact, the bolts have been bonded in there as well. I want to make sure I represent this in as accurate a way as possible. So I'm going to change the type of contact that's there. And the first step in that case is to come here and select all of these geometrical representations of bolt. This I could have done in my CAD package. So if you have geometric representations of bolts, especially if they have threads modeled into it, that not only is going to provide a less accurate analysis because of the contact situation, it's going to drastically increase your analysis time because it's going to model all the complexity of those little itty bitty threads. So I delete those because what I can do with an Inspire is put Inspire fasteners in there. And when I select fasteners, it's going to automatically locate holes that pass through multiple parts. It's going to find through holes that pass through other parts and blind holes that pass through at least one part and then partially pass through another part. And when I click Fasten All, it's going to put bolts in the through holes and screws in the blind holes. And if I select these, you see it will automatically calculate the allowable force on there because it is calculating the size of this based upon the hole and allowing me to apply a material to it. But most importantly, if I come back to my contacts, you see all of the contacts that were affected by the creation of those bolts and screws have now been changed to green, which is contacting, or what we refer to as a sliding contact. Those two surfaces can slide against each other. So being no longer bonded, it's going to force the stress, this force load to be passed through the fasteners, which is the actual accurate way to do it. And to make it even more accurate, if there's a possibility that in the process of applying a load, say to this arm, it could separate from this, because right now with the contacting, it can slide along but never separate. When I come to my analysis, I can turn on sliding with separation. Then it will continually check all sliding or contacting contacts and see if the forces at that contact would dictate a separation, and then you'll see it. This can add time to your analysis, which is why it's off by default. And if I've got two contacts that will never separate from each other, I just leave it off. But if there's the possibility, turn it on and improve the accuracy of your results. Okay, so that's how we deal with contacts and multi-parts. What this is all leading up to is where we want to go now, and that's to come back to our aircraft door hinge bracket and optimize it. We want this part to be as lightweight as possible, and we know our current design is over-designed, so there's some drastic room for improvement. If you're not familiar with topological optimization, which is the technical term from this, if you've heard the term generative design, that's kind of a new phrase that's come about that many people, many other softwares are using as they attempt to copy the topological optimization that Altair has been doing for 25, 30 years now. They want to tag a different name to it. So it's the same thing. We could call this generative design as well, but we like to refer to it by the scientific name, which is topological optimization. What topological optimization is the act of taking a part and removing unnecessary material. The easiest way to understand it is to think of it as sculpting. If an artist wants to carve a sculpture, they're not creating a sculpture, they're taking some sort of material and they're carving away the extra material that lies around the sculpture that's already inside that material. So they're removing material based on aesthetics. What Inspire does with topological optimization is it removes material based upon design criteria. And just like an artist would never take a current statue and carve a new one from it, we don't want to take a current design and optimize it exactly as is, or we're limiting the shape of our design. Because it is a removal, a subtractive process, it can never go beyond the bounds of my design space. What I want to do is create a big block of material that entirely fills my design space and get my most robust design from that. Now, everything I'm going to do here could be done in your CAD system, but I think you're going to find that the tools that we have in Inspire are actually easier to use. So I'm going to come to the Simplify tool, and I'm going to come to Holes. What I want to do is fill this pocket in. Holes is designed to find holes, and when I click on them, remove them. But all the holes I found, I don't want to touch. I want to get this hole here. All I have to do is double click on it. And when I click on it again, it fills it right in. And that's why I say this is probably easier to do than your CAD package. But again, I never discourage somebody from doing the geometry manipulation or design in the software they're most familiar with. Just make sure you leave the analysis and optimization to Altair, the experts in the field. So now that I've filled those in, some other things that they've done to lightweight this is to carve off the corners. I can very easily remedy that by coming to this tool called push-pull. Push-pull is literally that. I take a surface and I push it or pull it, and if it's angled, I can pull it all the way down out to a 90-degree angle. And now this is a good, nice, well-created design space. It is a big, blocky chunk of material that will give the solver the maximum capability of removal of material. Now, because this is a subtractive process, the other thing that I need to make sure I do is design this design space to be reflective of the areas that I can't move into. So this door hinge has a clevis style mount on it. So it's going to be a U that's going to come in on either side of this, and then some sort of bolt or pin is going to fit through there. So I want to make sure I don't have any material for my design space where that hinge is going to come in. And then as this swings open, it possibly could interfere in this area here. So this has been carved out of the original design, and I'm going to leave that as is. I'm not going to add material to that because, again, we want to remove or leave out material where we can't have the material. And these boxes here, these are put in so I could put a tool in here and hold on to the top of that bolt as I tighten it in place. So again, I'm going to leave that out of my design space. And when I have a design space I'm happy with, the next thing that I need to do is preserve the aspects of the design which have to be there. So in every case, every time we do a design, there are aspects of the geometry that cannot be removed. This is, as mentioned, subtractive. It will start carving away unnecessary material. Well, you can imagine what would happen if it started carving away material and began to eat into this hole here. Suddenly my part would be entirely unusable because I couldn't put a pin or a bolt through that and attach it to the hinge if there's no material to support that. So the areas where I load or connect to other parts, we're going to partition them into what we refer to as non-design space. And I do that using the partition tool, select on the feature I want to preserve, select the thickness of that feature that I want to preserve. It creates an entirely separate geometry, which allows me to right-click on this and set this now as my design space. It will turn red. Anything in red is design. Anything that remains gray is non-design. When you see the ultimate result of this analysis, you'll see that I will end up with this exact perfect cylinder here, and the other things that I need to do, which are to preserve these bolt holes down here. So I'm going to come to partition. Because it's selecting that entire pocket, if I were to select that, it actually will preserve the pocket. But like I said, I don't need this to be a perfect cube. I just need to make sure I don't have material there. So I don't need to affect anything in the cube. I just need my bolt hole. So I'm going to come to partition. If I hold my control key down, I can remove these horizontal surfaces, which separates the design space from the non-design space. And I can select that and preserve those. And I can go around and do the same thing to the other 4 holes here by coming back to partition, coming and deselecting those, picking, rotating around, deselect that, come here, and now I've got my geometry the exact way I want it. A nice big blocky bulk of material and all of my non-negotiables, my important regions protected. Now, because I started from scratch, I did lose all of the loads and constraints I put on there initially. So I would need to come and create those as well. I won't bother with that because I'm actually not going to run this optimization. An optimization like this would probably take about 5 to 7 minutes to run, and time is precious here, so we don't need to sit and stare at it run. I'm just going to bring up the results of that. So I won't bother creating the loads and constraints. We went through that already. But one more thing I need to talk about before we get to the actual optimization parameters, what we call shape controls. So I mentioned when we were talking about that VW part in the slides that a part that is incredibly well designed is completely useless to us if we can't manufacture it. And while additive is changing the way we create things, it's not quite ready to replace all of the other standard manufacturing processes, primarily casting, stamping, and extruding. So to make sure my part adhered to those manufacturing constraints, I could come here, select that, and I can pick the type of manufacture that I want to do. Single draw, which is a one direction cast or stamp. And you can kind of see what it does here with this shape. It allows you to create this type of shape, which has tapered in edges, so that the casting process, you take some sort of cavity, a negative space, you fill it with a liquid or semi-liquid material, allow it to cool, and then you have to somehow get it back out of the die. And if this had walls that went in the other direction, or a hole that passed through there, we couldn't get it out of the die. So it makes sure to maintain that. Split draw is basically just taking two of these, putting them together, and providing an indication as to where they part, and it allows things to come out as long as they meet at the parting plane. Extrusion guarantees I have a constant cross section on my part. It is primarily for situations where I need that constant cross section, and the majority of the time it's used when I'm looking to laser or water jet cut. And then finally, overhang, which is an additive manufacturing constraint to guarantee that I don't get more angle of overhang, thus requiring supports to make my part. This part, though, we're not going to apply manufacturing constraints because we're going to let it freeform and see what it comes out with. What I am going to put on here is what we call a symmetry constraint. Symmetry constraints, when I select the part, it's going to put 3 planes of symmetry on there, 2 of which are nonsensical. So I'm going to turn them off. But this now guarantees that my part is symmetrical. And by making it symmetrical, it will optimize it to make sure it's strong in both directions so that I can flip this part over and use it on the opposite side of the door or on the opposite side of the aircraft. So I get a single part that's utilized on both sides of the aircraft. Oh, turn those off. Oops. Turn that one on. And now I get symmetry across my part. Before we talk about the optimization, let me just remind you one more time again, if you go to menti.com, enter in that code 562036, you can ask any questions about anything that we've talked about here, or anything that you can think of. I'm looking forward to handling your questions in about the next 10 or 15 minutes. So we've got the part set up. Last thing we need to do is define our optimization parameters. So I do that by coming to my optimize button here. I click run optimization. And you see it's a topology, a topological optimization. And now I can set the parameters for that. The 2 main things we need for any optimization are an objective, what are we looking to achieve, and restrictions, constraints, what do we have to hold to achieve that goal. The 2 main objectives we'll talk about are this one, maximize stiffness, and the other, minimize mass. So maximize stiffness is going to be a topological optimization where we are going to make the part lighter, but the ultimate goal of the optimization, what it's targeting, is the stiffness of the part. So stiffness becomes a factor. It will remove material, or it will make sure as it removes material that the part is as stiff as possible. And if all I had was that objective, the optimization tool would come around and it would say, okay, wait, your part is as stiff as possible. So I need to give it some sort of restriction. And in this case, the restriction is a material utilization. I am telling it it has a mass target of 30% of the total design space volume. So this big red block here, I'm only allowing it to utilize 30% of this material, and that 30% has to be organized or arranged in a manner to make the part as stiff as possible. Why 30? Well, because in the 25 plus years that we've been doing this, we realized that 30% is a really good starting point. It doesn't mean that that is ideal for every single analysis, but it's a good place to start. And then as you begin to see the results, you can adjust up or down accordingly. Additionally, I can apply frequency constraints. So making sure that my part doesn't vibrate at a specific frequency. I can either say, just make them as high as you can, or I can say, I have a minimum frequency requirement of 100 hertz, 100 hertz, and all of the lowest 10 modes have to be above 100 hertz. Finally, I define my minimum member size. That is how small any feature that's derived from this can be allowed to get. And you'll see what that means when we get the end result. And then I click run. Or I could choose minimize mass. And you see minimize mass now uses mass as a target. So its goal is to make the part as light as possible. I don't have to tell it how much it gets. It's just going to go to try to get rid of as much as possible. But again, because optimization is tricky, or not tricky, it's sneaky. If I didn't do anything else, it would get rid of all of the mass and say, there you go. It would just leave the non-design spaces. So I have to set some constraint, and in this case, the constraint is a stress limit. So I put in a safety factor here. I believe in this one, we're going to use 1.5. Which means the software is going to start the analysis. It's going to look in the material. It's going to find the yield stress of the material. We'll divide it by 1.5 and set that as a stress limiting factor. So as material begins to get carved away, the less material, the higher the stress. So it's going to continually check that stress. And if it finds that that stress is raising as it removes material from this location, it's going to say, well, maybe I shouldn't get rid of it from this location and move somewhere else. So my end result will be the lightest possible part that will survive whatever safety factor times the worst case scenario of loading. Everything else remains the same: frequency constraints, supports, speed and accuracy, context, and then I would click run. Now, like I said, this would take about 5-7 minutes to run. So what I'm going to do here is just come to the end result, which is this. Nope, not that. Sorry. This right here. This is what it comes up with. Now, when I said minimum member size, that's these guys right here. It does not allow the size of these members to go below a certain value. Whatever I set there. If looks a little bit thin to me, so I can always increase this a little bit by sliding this little slider over. And once I have that, now I can come here, click Analyze, and it will take my result, my shape, my topologically designed shape, utilizing the forces that were put on there, the constraints that were put on there, and it will run an analysis so I can see how this part is going to behave. While it's going through this, and this should just take a couple of minutes, a couple of things worth mentioning, and something most everyone notices immediately is it has abandoned these two bolt holes. Well, why has it done that? In the case of this part, it was run with a minimize mass objective. And remember, with minimize mass, it's trying to get rid of any unnecessary mass. And what determines whether mass is necessary or not? Stress. And so what it determined was having mass to connect to those bolt holes did not do enough to limit stress. It wasn't necessary. It was limiting stress enough by connecting here and connecting here, so this kind of intermediate point was deemed unnecessary, so it used the mass elsewhere or just got rid of it altogether. Had I run this with maximized stiffness, it would have absolutely grabbed onto those. because it will grab onto anything it can to maximize stiffness. And what people will do quite frequently is to run both of them and utilize information garnered from both runs. I cannot stress enough, no matter what other companies who do this topological optimization or generative design may try to convince you, a software is not going to design a part for you. It is not the job of the software to do the job of an engineer. It is an engineer's responsibility and ultimate responsibility to design a part. A software like this is a design tool. It helps you understand information about your part, but then you take that information and you engineer a part from it. And that's what we can do if we run both of them. We can then engineer a part with features that maximize the stiffness and features that reduce the stress. And since we're done here, I just click this. I'm going to come down to my von Mises stress. You can see there is a lot more stress on here, which is understandable because there was virtually none on the original part. So my final check here is to come to my factor of safety. You see I'm not hovering at 6 across the entire thing. I can begin to reduce this. I have a far lower factor of safety for a large majority of this part, but you can see I'm still up in the 4, 3.5 range. And as I keep coming down and coming down, the amount of material is decreasing until I get down to 1.5, and everything essentially is gone. Yes, I still have some areas which have a slightly higher stress, but you'll notice most of those occur at these sharp corners, which are just part of my design space, because again, this isn't the final step. I'm going to take this, I would round out those corners and get rid of the majority of stress in those areas. What now? Well, I can take this and I can click, make sure it's nice and a robust design here. I can click Fit Polynerbs. It will create a solid polynerb copying or following the general shape developed by my optimization code. And now this is all geometry. I can take this, send it to my CAD system, work on it in there, or I can, inside of Inspire, come here to my polynerbs. We have this tool called Wrap, where I can take and create these little tubular members here, bridge them together. So if I have that, and we'll come up to here, so I'll grab right here and come to right there, and then I can bridge these together. So I can say, okay, come from here to there, and it will connect them together. And then if you get really good at that, you can ultimately create a part that looks like this. So this geometry was entirely created within Inspire. So you have that option to go there, or you can do your geometry creation in your CAD package. So I know we're right here at the bitter end. One more thing I just want to mention to you is we do have the capacity to do motion analysis. That is an entirely other class. But what it will allow you to do is something like this, where we can simulate the kinematic dynamic motion of a system, and we can use that then to feed into a structural analysis or optimization. So this is a motion analysis. I put some actuators in there to lift the spoiler. I put some motors on here to begin turning this. These joints were all automatically created. I did not put a single force into this. The behavior of this little member here is driven entirely by the forces calculated at all of these joints as a result of the mass of the part and the motion that it is going through, and it then fed that into an analysis. So what I want to leave you with here is we do support teams. As mentioned in the introduction, we support teams through providing free software. You can go to altairuniversity.com. On there, you'll find our sponsorship application. I say application, but you don't even have to apply. You just put the information in, and it's more like just signing up than applying. You'll get a word back from us where they will get some more information from you, and you'll get your licenses usually within about a week or so, pending just some signing of documentation. And with that, you will get training, you will get support, you will get mentoring. We have a student edition as well, where you can get this free. Again, altairuniversity.com. Make sure you stop by there, and we can provide you training information as well. So I appreciate your time watching this. I will now pass it back to Norman, who will wrap things up and begin the question and answer session. Hopefully, he's got a nice big list of questions to pose to me, so he'll ask me, and then I'll answer to you. Appreciate your time watching this. Take it, Norman.
Sorry for that. I was still amazed and mesmerized by your presentation, Eric. Thank you so much for the insightful and for the thoughtful presentation. Very detailed, and we have a great number of questions coming in. Really lots of detailed questions as well. I hope they push you a little bit to the limit. But folks out there, we have nearly 40 minutes, so please keep the questions coming in. Use menti.com, enter the code that you see on the screen, and keep asking your questions. I will fire them away to Eric, and let's see if we can push him to the limits with your questions in this call. But first and foremost, can you say a little bit, do our students need a powerful computer to run the software?
It's a great question, and I'm glad we started off with that one, because that's a really important question, and the answer to that is absolutely not. Inspire was designed to be very processor and graphic friendly. It can run on pretty much any computer that has the capacity to run Windows 10. Now, that being said, obviously, in any situation, the more powerful computer you have, the faster processor, the more RAM, the better graphics card, Inspire will run better and faster on those. But for functionality, pure functionality, I've even worked with customers and installed Inspire on like a Microsoft Surface tablet computer, and it is run perfectly fine on there. So whatever computer you have, it will run on there. Just know that the faster the computer, the better it will run.
I think that's the usual story with computers these days. And you already explained at the end of your presentation how the Shell Eco Marathon teams can get hold of the sponsorship from Altair. But we have a more specific question to that point. Do we get Altair Inspire software for free outside the trial version? And can you explain the difference between sponsorship and the free student edition?
Another excellent question. I'm glad that was asked as well. So first and foremost, there is no trial version of Inspire. The two separate types of Inspire, well, three separate types. We, of course, have our paid corporate version of Inspire, our student version of Inspire, and our sponsored version of Inspire. The thing about it is all of them are 100% fully functional. In fact, the sponsorship version of Inspire is exactly the same. It runs off the exact same type of license that our corporate level does. But from a functionality standpoint, there is absolutely no difference. The one slight change is because the student edition runs off of it's fully functional, but it runs off a student license, which some of our other software does have some limitations, it usually ends up being about a release behind our corporate level version or our full sponsorship level version. So if you want to run the absolute latest and greatest version of all of our softwares, the sponsorship's the best way to go. They are all free. The sponsored version and the student version are free. Student version is more for an independent person, but the team sponsorship, Usually it's the team captain that signs up for it. You'll find that form on altairuniversity.com. And when you go there, they'll sign up for it. In about a week, we'll have the license, and you can get as many licenses as you want. You have 2 people on the team that want to run Inspire or any of our softwares, we'll give you 2 licenses. Everyone loves it so much. You have 25 people on your team. Everyone wants to play with it. We'll give you 25 licenses. And if you have a major recruiting drive and you get 5 more people, just drop us an email. We'll get you 5 more licenses. So the sponsorship is definitely the better way to go if you're on a team, because not only do you get the full corporate, you get as many licenses as you want. Plus, we're going to treat you like a customer. We're going to give you training. We're going to give you support. We're going to help you out. Whereas the student version, it's still a fully functional, but any support that is going to come from our forum on our website. You can't contact support directly, whereas with the teams we work with you directly. So
thanks very much, and that's really good to know that this is the way to go to get the latest version of Inspire to work on from Altair. Now we'll get a little bit more technical, Eric, here into the presentation. And the first technical question, can you use Inspire for more than castings and additive parts, specifically sheet metal and tubes for frames?
Very good question. So sheet metal, we do support sheet metal. If you have surfaces in your geometry, they will come in as surfaces in Inspire, and then it's just a matter of clicking on that surface. Of course, we'd have to add a thickness to that, and that would just be in the property editor area. So it does not have to be solids. It can be surfaces, and with a tube, you actually could do it as either a solid or a surface. You would just thicken the solid, or the solid would represent the hollow version of the tube, whereas the surface would just be a cylinder that you would apply a surface to, and that we can do topological optimization with both surfaces and solids. So it just matters as to what the geometry was initially.
Thanks, Eric. And as lightweighting comes not only with the design but also with the material, some of our teams are asking, can Inspire work with composite materials?
Yeah, excellent. And I get this question a lot because composites is the way things are going these days. They're strong, they're lightweight, they're durable, they don't suffer from rust. So the answer to that is it's yes and no. As I'd mentioned when we were talking about the generation of the materials within Inspire, Inspire does require a linear isotropic homogeneous material. Its strength is simply defined by the Young's modulus, which means it assumes it's the same in all directions and throughout the entire thickness, which of course we know that composites are not. Composites are of course a layup of plies that have multiple angles. But in most cases, especially with a lot of the design teams, what they're doing is they're creating a composite layup that can be simulated as an isotropic material, because for every 90 degree, they have a 0 degree and another 90 and another 0. So we can simulate an isotropic material from it. So what you essentially do is you take the composite, you homogenize it, come up with an overall strength of material with a general Young's modulus to it, and do that. Or they just run it as a standard homogeneous material and take the design that it comes up with and then use composite to create that design. So while we can't directly support composite, and I'll say yet, because I know eventually it's going to come, we still can work with composites by just assuming them to be a homogeneous material at this point in time.
Mm-hmm. Thank you, Eric. And again, the questions get a little bit more specific. So let's see where we get with your answer. There's a question around the holes. So do holes have to be made in the CAD model in order for Inspire to recognize them as holes, or also as negative extrusions? Will that work?
So when you bring the geometry in, the geometry is going to come in as it was. So it will recognize a hole as some sort of relative circular entity. They don't have to be perfectly circular or cylindrical. They can be a bit more oblong, kind of like an ellipsoid hole. As long as, and I don't know where it would kind of stop recognizing it as a hole and start looking at it as it more of a slot. But I've seen it work with ellipsoid type holes. It's just as you get more and more of a flat in between the two semicircles, it would stop thinking of it as a hole and thinking of it more as a slot, and it wouldn't recognize it as, I'm assuming we're referring to things like loading and constraining. As for the reverse extrusion, I'm going to have to ask whoever asked that question to just kind of elaborate a little bit more on what they're talking about with that, to make sure that my answer is correct. So if whoever did that can post another question and just kind of flag it, and then Norman can kind of keep an eye out for that for an elaboration. I'll see if I can circle back to that question and answer it.
Yeah, we'll do that. I'll look out for that question. And
great.
The next question, I was wondering if it is possible to sketch a model in the software and build the model from the ground up, or can we only make simulations to test the said model?
Excellent question. And I think what I'm going to do to answer that is I will talk to it, but I will also open up the software. So I'm going to come back and I'm going to show you. So the short answer is yes, we can sketch directly within Inspire and create the geometry. So I'm just going to eliminate this. I'm going to come to a blank screen here. So I'm going to start this, but I'm going to put the caveat out there right now. We are not a CAD software, and at the moment we're not trying to be a CAD software. So the tools that you may be familiar with in CAD, we don't have the extent of that. We aren't parametric. We don't have a design history, but we absolutely can generate geometry within Inspire. So from this, what I can do is we come back to geometry, and these are our sketching tools, and I would pick one of them, and these are multifunction. So say I want a sketch a rectangle. It will give me a plane here. I can sketch that rectangle. It'll put dimensions on there. I can alter these to be whatever I want. We'll say 150 by 100. And then I can right-click to get out of the sketching mode. I can sketch some other things on here, or right-click again, and I end up in what we call the push-pull mode, which we saw earlier. But now I can take and extrude that out into 3 dimensions, and I can make that as long as I want. And I can always come back and alter that length again with push-pull. But now that I've got geometry on here, if I come and sketch again, so I'm going to come to my polyline, I'm going to sketch on this surface right here, and I'm just going to say, okay, we'll come to here, here. We'll make some sort of really kind of interesting sketch here. And now if I connect that, again, right-click to get out of there. I can take and pull that out, or I can push that back through, and I can create my parts that way. So we begin with a simple sketch and then begin to add or remove from that sketch, creating fillets on there so I can round the edges, come through here, give it a size, we'll say 9, and it creates nice little multi-rounds at the corners here. But this is what is typically referred to in CAD as a dumb solid. Dumb solid is it has no history to it. I can change this, but I have to come to it individually, grab that and change the radius there. I don't have a design history tree to come back to. So short answer, yes, we can do it. Long answer is it's a little bit more complex than a standard CAD system.
Mm-hmm. Thank you, Eric. And again, a reminder for all of you, if you have questions or if you want to build on any further questions, now is the time to enter them. Go to menti.com, enter the passcode if you haven't already done so, and type your question in there for Eric. So we still have a good 25 minutes here in the Q&A session. Next question. Does the force boundary condition imposed on the cylinder surface work like force in ANSYS? We don't want to exert any tensile traction there. In ANSYS, we would apply a bearing load there.
Excellent question there. And to answer this question, I'm also going to come back to the software here. And just quickly, what I'm going to do is I'm going to put a hole here, so we'll have something that I can work with. So there, I've got my little hole here. When I come to my force, when I put this here, what it's going to do is it's actually going to create a force at the center of the geometry. And what you're not going to see, because we just don't want to muddy up the picture, but what's going to happen in the background is it will connect that force using what is referred to as an RBE3 in OptiStruct. And an RBE3 is a rigid body element. It's a flexible rigid body element that will take this force and distribute it to the entirety of the inside of that. So it will not have bearing or traction force. It will be purely a force that's put here but then transmitted to each point on there. But interestingly enough, if I come back to this force, I can actually change that. So you said you didn't want it, but in the case that you do want a bearing or traction, I can come here and I can say, I want this to be a bearing load. Now we get that cosine distribution, and I can orient that in any orientation around there. So I get that nice bearing load, that cosine distribution of the force. Or I can change it to a traction load that's now going to be normal to or tangent to the surface all the way around, and I'm going to get that traction load in there. So the default one will not be a bearing or traction, but we can very easily convert it to either if you so desire.
Mm-hmm. Thank you, Eric. And another question on the load cases. Can you choose only one load case for the buckling mode analysis per analysis, even if you were analyzing more than one load case in your analysis?
Yes, when you go through, and again, I'm going to come back to my software here. So when I come to analyze, and actually let me put one more force on here, or it doesn't really matter what it is. I just need it to be a separate load case. And we'll take that off of there. When I come to analyze and I come to buckling, and I select that, I can select one or both of the load cases. And what it essentially does in the background, and I don't want to get too far into the weeds here, but it creates like a superposition load case where it will actually combine all of these into one single load case. Because to run a buckling analysis, you can actually only use one load case. So in the background, and you don't need to worry about it because it does it all on its own, it will take all of these and then combine them into one load case, or I can just select one and it just uses that. So I can do one or I can do many, and it will make all the adjustments in the background to make sure that all of those loads and all of those load cases are combined to get an appropriate buckling response.
Okay, thank you very much. And again, more on the loads. Can cyclical loadings be applied in Altair?
Cyclical let me take a step back from that. So yes, we could apply a cyclical load on it, but actually one of the better ways to go about doing it is to apply a cyclical symmetrical constraint. So again, I'll keep popping back to the software, but I think it's the best way to go about doing it. If I come back to my shape controls here, so I can come here, we talked about symmetry, which was just pure planar symmetry, but if I do cyclic symmetry and then apply it, what it will do, and this obviously doesn't apply to this part because it's not cyclically symmetrical, but imagine, a gear or something along those lines. So if this were a gear, I would increase the number of sections so that each one of these met one of the teeth. I would put forces just on one of those teeth, and then what it would do is to guarantee symmetry, cyclic symmetry, everything that it did for maintaining the structure of that tooth, it would have to then apply that same geometric generation or that same topological optimization to each one of these different teeth, because it has to adhere to the cyclic symmetry. So what I've seen people do is they just apply loads to the one location, and then the cyclic symmetry will drive generation of geometry in the other locations as well.
Mm-hmm. Thank you. Coming back to the design part that you talked about and that you showed, one of our viewers is asking, why didn't you apply a plane constraint under the part, in addition to the constraints around the simulating the fastness?
Oh, very good question. I just didn't. For simplification purposes, I didn't. But what that ultimately did was it allowed a slight amount of penetration at the corners. But the problem and the reason why I didn't do it is because those 6 constraints that went around there were actually enough to handle it, and the slight penetration that I would get was within reason. I didn't need to take that into account. But what would have ultimately ended up happening is, had I applied a planar constraint on the bottom of it, because of the limitation of constraints, I can't tell it to constrain it only in the direction that it's applied, and not in the other direction. So the plus, and you know what, I apologize, but I'm going to come back thing here. My model. If I apply a planar constraint on the bottom of that, that means that yes, it can't penetrate down, which is what I want to simulate, but it also means that it can't lift up, because a constraint is just in this case, the y-axis. There is no such thing as a positive or negative constraint, which meant I might get some phantom stress in this area, especially with one of those that was trying to bend the part back. So by not putting that on there and realizing that, yes, it could not penetrate down through, but it would eliminate the phantom stress I would get as it pulled back, to me, that was a bigger benefit than it was detriment of allowing it to slightly penetrate down through.
Thank you, Eric. We have somebody asking, does Inspire work on Mac computers?
You know, I don't believe so. In fact, no, I'm going to take a step back and say no, it absolutely does not. I think we ran it on Mac for a while, but there just wasn't enough of a use case for us to go through and do all the QA and porting and everything. But so native, it does not. We do not have a Mac install. But what we found was a solution to that was to be able to run, if you can run a Windows emulator on your Mac, and we have dozens and dozens of people within Altair who are Mac devotees, and they just run a Windows emulator like Boot Camp or Parallels or one of those, and there are some free ones out there. Because Macs are using the Intel processor now, all you have to do is run the emulator on there, and it runs perfectly fine in that case. So no native, but very easy to do by running an emulator. In fact, the president of our company is a big Mac user, and he emulates through that. So.
Okay, thank you. That's clear. And we have the follow-up question to the original one about the extrusion and holes.
Okay, excellent.
The team has come back and said, my question regarding the holes was, what I meant was whether we need to use feature-based CAD in order for our geometry to be perfectly recognized by Inspire, or features based on 2D designs are compatible too.
Okay, yeah. So the feature-based CAD, what's going to happen when it comes into Inspire, whatever the condition of it in your geometry tool, when you convert it out, all of those, anything feature-based or anything parametric is going to be lost. It's just going to come in as a general dumb solid. So essentially, get your geometry into the position or into the shape that you want it to be, and then it will come into Inspire in that method. So you don't have to have parameterization. You don't have to have feature-based. You just basically set it up, define your parameters, define your sizes, define your dimensions to whatever you want them to be, and then it will come into Inspire as that dumb solid. Not really a big fan of that name. It sounds derogatory, but it's a solid without history. So it will just come in that way. So however it looks in your CAD system, that's the way it's going to look in Inspire, and then it becomes an Inspire solid, so you can manipulate it in Inspire after that.
Thank you. Again, quick reminder, we have about 15 minutes left, and if you still have any questions that you want to ask Eric about Inspire, bring them in now. Go to menti.com and enter the passcode. Your chance to get your question answered. A team is asking, is it possible to optimize a 3D printed part with a shell, say 2 millimeter thick, and a support structure inside, say a 30% filling?
No, that we can't do. Any filling is going to, or inside support structure is going to have to be generated by your printer. When we optimize it, we have no way of telling it what to do on the inside of the part. So it's going to come up with an optimized shape, and then you'd have to set that up with your 3D printing software as to what's going on in the inside. But the only design constraint that we have, or manufacturing constraint that applies to additive manufacturing, is that overhang. Now we do have a feature that last pull down on the upper menu, Print 3D, which will allow you to create slicing directly within Inspire. Right now it's just metal based, but ultimately it will be polymer as well, SLS type metal based. Where you can do that and simulate the printing. But from an optimization standpoint, it treats the solid as a solid. It may go hollow in some places on the inside, but that's just how it determines which elements are necessary and which aren't. We have no way of driving that. But it's an interesting point you bring up, and one that, based upon your question, I will take to the design team for Inspire, because I think it's something that they should probably start thinking about. So I appreciate the question. It did raise something that I'd never thought of before, and I'll make sure to mention it to them and see if maybe sometime in the future, I know that won't help you now, but you may ultimately have a little bit of an effect on the development of Inspire in the future.
And thinking about work efficiency, do you have any thoughts on whether, if you have an existing part that you would like to improve, should you first run an analysis or should you start with the optimization?
It really depends. As I'd mentioned, there is no absolute necessity to run an analysis first. I did it on this because I did not know the behavior of my current part. But you may be so intimately familiar with your part, and maybe you've even run tests on it and used it in a practical aspect, that there's no need. You're not going to gain any information from going through and setting up an analysis. So don't bother. But if you need to know, or if the results of your optimization are going to be dependent upon knowing the information about your current part and you don't know it, then yes, you absolutely would run the analysis first. But many people don't even bother with an analysis. They just jump straight into optimization. And I can't stress it enough. If you've got a current part, remember, don't just take your current part, put the optimization parameters on there and go. Think of it again as, I'm not going to carve a statue by taking a current statue and carving a new one from it. You want to take your current design, you want to build that big bulky design space out of it and then optimize it. But to answer your question, no, you don't have to run an analysis first.
Mm-hmm. And somebody is asking, is no mesh required to be input by the user?
No, there's absolutely no requirement for the mesh to be input by the user. Inspire is using SimLab, our feature-based batch meshing tool, as a meshing engine. It is feature-based, so it will intelligently look at the shapes of your part, the geometric features of your part, and it will create a varying size mesh to accommodate those features. It will come up with a rough element size, and then create a varying size mesh on there. I will mention one thing, though, if we can pop back here to my screen, or to my software. So with this right here, we do have the ability, if you come to structure and we have this little setup thing here, we have control. Even though I don't have to, and it will create an adaptive mesh, I can do mesh control. I pick a surface and I give it an element size. So I would say I want this surface to be 3 millimeters. I want this surface to be 5 millimeters. So I can create some mesh control in here and then it will use this as a global element size, but it will allow me to use my low, and I think I didn't save them before oh no, they're still there. Good, okay. So it will use the global element size, but then adapt based upon the things that I put on there. So it creates a great mesh on its own. I think actually if I come here, if you just bear with me for just a second here, I can come into the solved. I need it to be solved because I need to be in the post-processing. But this little icon here, which appears when you're in the post-processing, actually shows me the mesh that was created on here. And you'll see that the elements in this area are actually larger than the elements in this area because it is adapting the mesh to get 3 nodes across any surface. It creates a slightly smaller mesh in the areas of curvature to capture that. So it is creating a high quality adaptive size mesh as it goes through and meshes. So you don't have to do anything, but you do have the ability to control it if you want to.
Okay, that's clear. And again, we have a question building on a previous one. Remember the one about cyclical loading? The person who asked the question wants to clarify that what I meant with cyclical loading is the application of repeated or fluctuating stresses. Can you test these kind of loads?
No, okay. Okay, yeah, my apologies for interpreting your question wrong. And unfortunately, the answer to that is no. This is a static loading situation. Any dynamic loading, we can simulate it if you use the motion analysis to drive that dynamic loading situation. So that we get kind of a dynamic by basically stringing together a bunch of static loads, but that would be the only way to get any dynamic loading in there. Everything else is just going to be simple static loading, and I apologize for misinterpreting your question.
Mm-hmm. Okay, no, thank you, Eric. And does Inspire software support files created in Rhinoceros software?
Rhino, I believe, would be able to export in an STL format. I'm not intimately familiar with Rhino, but I would think because it's a kind of I think it does rendering and such, it would do STL. I know that, and we don't need to switch over to my thing, but I can just take a quick look here. I don't see Rhino in our list, but if Rhino does support like IGES, Parasolid, or STEP, we could bring it in that way. I unfortunately am not familiar enough with the Rhino software to know what the file types it can export out. But IGES, Parasolid, STEP, or STL are kind of the intermediate formats. So if it supports any of those, absolutely, we can bring it in.
Thank you. And I've got a couple more questions for you here, Eric, before we close out for the day. Is it possible to model and optimize shell structures like P-shell in HyperMesh?
Yes, yeah. So if you bring it in, if you bring your geometry in as a surface, it will do shell mesh on it in Inspire. And since you specifically mentioned HyperMesh, if you are willing to kind of devote the time to learning HyperMesh and OptiStruct as a whole, there are many more optimization opportunities or capabilities within HyperMesh and OptiStruct. Inspire represents a small subset of those, though that small subset is the most popularly used. There's much more you can do using HyperMesh and OptiStruct, but if you have surfaces, it will be shell meshed and it will optimize, do a topological optimization on those shells. And we also have topographical optimization on shells as well, which is a bead structure optimization.
Okay, that's clear. And the final question here for you, if I may, it is very relevant for Shell Eco Marathon because we see it more and more. Can we work with foam or any porous materials?
When it comes to material definition, it is required to be an isotropic, heterogeneous material. So if you can come up with a linear definition of that would be able to be put into the Young's modulus, yes, but if it's elastic in any way or nonlinear, we wouldn't be able to. So you would have to come up with it. I mean, I don't know if you look closely, but I put in a Douglas fir material in there, which was just kind of a generalized. Wood is obviously, because of the grain structure, it is slightly porous. It's not truly linear, but I was able to kind of linearize it and get a general behavior. So as long as you can come up with a linear representation of it, a homogeneous representation, you could use it, but it will not be truly analyzing the porous type material.
Mm-hmm. Thank you. And I've seen a question coming in several times also from several of our viewers tonight. Will this session be available? Yes, you will receive a link for the recording of this session. So please, by all means, share them with your teammates, with your peers, or with anybody at your university you think might find it interesting to listen to this presentation from Altair. Eric, I would like to thank you so much for the time today and for giving us this amazing presentation and all your very detailed answers to the questions. Thank you so much to you and to Altair for this presentation.
It was a pleasure.
And thanks everybody on the line here today for taking part and for tuning in. There are more virtual sessions coming up in May. Tomorrow we'll be hearing again from Eric about fast meshless analysis. But if you haven't registered yet for this or any other webcast, please go to our website and register. We'd love to have you and to join us. But until then, I wish you a very good evening, a remainder of the day, and goodbye from me. Bye-bye.